Our next topic in our progression through fluid mechanics is the Bernoulli equation, which is simply a special case of the Euler equation that we derived in the previous videos. It's named after Daniel Bernoulli. As with most of our fluid mechanics, we typically name things after people that first discovered them or developed the concept. For example, the Lagrangian perspective, the Eulerian perspective, the Euler equation, and now the Bernoulli equation, and there's countless others beyond that that you'll see as we progress through the class. So the Bernoulli equation was derived by Daniel Bernoulli in 1738 when he suggested that we integrate the Euler equation along a streamline for a steady incompressible flow. Okay, so what we're going to do here is start with the Euler equation and then do the derivation that Daniel Bernoulli did. Okay, so what we're going to do is start with the Euler equation, where we take our cylinder that we used that was at an arbitrary axis S with an angle alpha from x, and just rotate it back to that x direction without loss of generality in this case. So it's more like the special case example that we did, where the cylinder is exactly along the x direction, and from there we can write out the Euler equation, which is going to look like this. It's going to be negative d over dx of p plus gamma z is equal to rho a x, the acceleration in the x direction. And the first thing I want to do is rearrange it slightly and divide through by the specific weight of the fluid, gamma. So let's do that. So we're going to have negative d over dx of p over gamma plus z is equal to, and recall that the specific weight of the fluid is simply rho times gravity. So we divide through by gamma, we're going to get a x over g. Okay? So this now gives us a familiar form, ax over g, that is related to that special case again that we did before, which is the slope of the lines of the constant pressure. So we have that slope ax over g. All right? So the next thing I'd like us to do is let's think a little bit about the acceleration in the x direction. If you recall from the video on acceleration, ax is equal to du over dt plus u du over dx plus v du over dy plus w du over dz. And so now we're going to make our first assumption. We're going to assume the flow is steady, just like Bernoulli posited up at the top of the slide there. So if we assume the flow is steady, then our unsteady term is 0, our local acceleration is 0, so we get rid of that term. Now we're going to make our second assumption. The second assumption is that we're going to say it's a two-dimensional flow. And by two-dimensional, what I'm saying is that w is equal to 0 and d over dz is equal to 0. Okay? So remember that, and immediately I think you see in the acceleration this last term goes to 0 because both parts of that term are 0. Okay? So we're left with ax is equal to u du over dx plus v du over dy. Okay? And what we want to do now is plug that into our Euler equation. So let's go over here. I'm going to plug it into our Euler equation, and we're going to get negative d over dx times p over gamma plus z is equal to 1 over g times u du over dx plus v du over dy. Okay? All right, so now we're going to make our third assumption, and we're going to assume that the flow in this case is irrotational, that the flow field is not rotating in any way. The streamlines are straight, and there's no, basically what it means is there's no spatial gradient in a lot of the velocities, and so there's no rotational component in the flow. So if you recall from vector calculus, we can use the curl of a field to calculate how much rotation is in the flow. And therefore the flow is irrotational if the curl is 0. So going way back to vector calculus, the curl of the velocity vector is the del operator, the cross product of the del operator and the velocity. And that is simply the determinant of this matrix, where the first row is the unit vectors in our 3 directions. The second row is the derivatives in those 3 directions, and the third row is the velocities in those 3 directions. So if we do that, we get dw dy minus dv dz I hat, du dz minus dw dx in the j hat direction, plus dv dx minus du dy in the k hat direction. Okay, I'm not going to spend much more time on that, but that's really what defines the rotationality of the flow. And for this case, what we're going to end up doing is setting that to 0. But before we do that, what I want to do again is go through what our assumptions tell us about these different terms. So if we look at the I hat direction, we have dw dy. We've already said that dw is 0, so this is 0. That goes out. The next is dv dz. We said d over dz is 0, so this is 0. Then let's look at the j hat direction. We have du dz. Well, we know that d over dz is 0, so that's 0. And then finally, dw dx. We know that w is 0, so this term is 0. Okay, so that was convenient. We got rid of a lot of the terms in this fairly complicated curl problem. Okay, so now we're going to go and look at just the k hat direction. This is the only component we have. We have dv over dx minus du over dy is equal to 0. And I want to rearrange that slightly because we're going to use this assumption of irrotationality to get an expression for du dy that will be an x derivative. So what we're going to do is say du over dy is equal to dv over dx. Right? Because they have to be 0, those two have to be equal. So du dy equals dv dx. Now we can go and plug that back into our current version of our Euler equation. We're going to end up with negative d over dx of p over gamma plus z, that part's not changing yet, is equal to 1 over g times u du over dx plus v dv dx. We just replaced du dy with dv dx. Okay? So the next thing we want to do is we're going to take a look at those terms. I'm going to write this out again real quick here so we have it. Again, it's simply negative d over dx of p over gamma plus z is equal to negative 1 over g times u du over dx plus v dv over dx. Okay? And what I want to do here is use the product rule. So what we're going to do is use the product rule. We're going to say u du over dx is equal to 1/2 du squared over dx. And that's really just using the product rule in reverse. And we're going to plug that into our equation here. And that's going to give us negative d over dx of p over gamma plus z is equal to negative 1 over g times 1/2 of d over dx of u squared plus, we're going to do the same thing for the second term, 1/2 d over dx of v squared. And now we have everything within our x derivative. So everything's with a partial derivative with respect to x, which means that we can now lump everything together. So I'm going to rearrange again and lump it all together. So what it's going to look like is d over dx of p over gamma plus z plus parentheses u squared plus v squared over 2g is equal to 0. So that's where we're at now. All right? So now it's pretty straightforward to integrate with respect to x, right? So if we integrate that, we simply get p over gamma plus z plus u squared plus v squared all over 2g is equal to a constant. Right? Now, we want to make a few more simplifications here. So the first thing we want to do right now is I want to look at this term here, u squared plus v squared. So if you recall what that means, u squared plus v squared is simply equal to the magnitude of the velocity vector squared, right? So if we have some velocity vector out this way, and we have u here and v here, the magnitude of that velocity vector is just u squared plus v squared, right? So we can plug that into our equation. So let's go over here. We can plug that in, and that's going to look like this. So we're going to have p over gamma plus z plus the magnitude of the velocity vector squared over 2g is equal to some constant c. Oops. Like that. Okay? So the next thing we're going to do is just drop some of that notation to clean it up a little bit, and we're going to say that the magnitude of the velocity vector squared is just equal to v squared. So just capital V squared. Write that out one more time. We get p over gamma plus z plus v squared over 2g is equal to a constant c. And this right here is the Bernoulli equation, okay? And you'll see it over and over again in fluid mechanics. This is the Bernoulli equation, and it is in your book, Munson. .7, okay? So I mentioned at the beginning of the lecture, or this video anyway, that the Bernoulli equation was one of the most commonly and widely used equations in all of fluid mechanics. However, it's also one of the most often misused. So it's applied incorrectly countless times. And the reason for that goes back to the assumptions we made to get to this point. And so I want to close out this video by going over those assumptions again, because every time you employ the Bernoulli equation, you should go through this checklist to make sure you meet all these conditions. And those are, we assumed to get here that the flow was steady. Okay, steady means that du over dt is equal to 0. So if you have any local acceleration, the Bernoulli equation does not work. Okay? The second assumption we made was that the flow was incompressible, and that was in the original statement by Bernoulli to integrate along the streamline. And that means that rho, the density, is constant. And for most of applications in engineering, that is going to be the case, that rho will be constant. But there are cases where rho is going to change in time, specifically like high-speed airflow, where air is actually somewhat compressible, and so again, the Bernoulli equation doesn't hold in that sense because rho is changing. Okay. The third assumption, again, is that the flow is irrotational. Okay, and irrotational means that the del cross V is equal to 0. Okay, and what that means is that there's no rotation in the fluid. And if there's no rotation, there can be no shear, and the viscous forces aren't present. And so that also leads into our last assumption, our fourth assumption, that we didn't explicitly state in our derivation, and that is the flow is non-viscous, that the viscosity is unimportant. It's effectively 0. So this means, this last assumption is that the viscosity is effectively, I'm going to not write that as an equal sign, is effectively 0. Okay? So if the viscosity is effectively 0, that means that there's no shear stresses. So recall that tau is equal to mu du dy, where nu is equal to mu over rho. If nu is 0, then mu is 0. So that tau is 0. There's no shear stresses, which effectively means that the only forces in the flow are pressure and acceleration. Okay? So that concludes our video on Bernoulli and the Bernoulli equation. Just remember that it is an extremely useful equation. We'll see that in some of our examples. But before you employ it in any engineering situation, go through your checklist of the assumptions. See you next time.